estamos já transmitindo? So it's okay? Okay, so thanks everybody for coming. So it's a pleasure to have Professor William Phillips here. So he was visiting USP as part of the International Union of Pure and Applied Physics. In fact, he's a frequent visitor to São Carlos, to Vanderlei Banhato in São Carlos, but I think not to here. So I think it's his first time here. So I think everybody knows he got Nobel Prize in 1997 for his work on laser cooling, together with Steve Chu and Claude Cohen-Tanuji. The people who were at his outreach lectures also know the other side of him. So for people who didn't go to his outreach lecture here, it's a whole, I don't know, it's like a circus presentation. So he told me that he has to drive his equipment in his car, so he has to modify his car to drive his equipment to where he's going to give his outreach talk. So I think it's something that we need to work on here, on having more dedicated people to do outreach. So it's a pleasure to have William Phillips here, and I hope we have a chance to interact with him. Thank you.
Well, thank you very much. It's a pleasure to be here at ICTP. So I'm thinking, should I put my jacket on? No, probably not. Let me ask you this. You heard that I'm here for the meeting of the International Union of Pure and Applied Physics. Before that moment, how many of you had ever heard of IUPAP? Okay, so I mean, that was what, maybe 10% of the people? So obviously it means we need to do a better job. IUPAP is an international organization of physics throughout the world, and I'm a member of Commission C2, which is involved in fundamental constants and units and things like that. And so usually when I give a talk like this, and I'm not sure I'm quite prepared to do this, I offer a prize to anyone who will ask a question. So the key thing here is that the reason I was thinking of this is that the prize that I'm going to offer is a wallet card of the fundamental constants of nature. So, and you know, it fits in very nicely with my role as a member of this commission on symbols and units and constants at IUPAP. So anyone who asks a question gets a prize. I hope that I have enough to give them. So since we're a relatively small group, and this is sort of an intimate room, I want to encourage you to ask questions during the talk instead of waiting until the end. And since you're a little bit in the dark because the projector is a little bit weak, either that or my eyes are weak, I might not see you if you raise your hand. So if you raise your hand and I don't recognize you within about 5 seconds, just say, Bill, I have a question, okay? And then I'll, maybe my hearing will be good enough that I'll be able to respond. Okay, so here we are, manipulating atoms with light, from spectroscopy to atomtronics. So I want to begin by saying that it's my great pleasure to work with Gretchen Campbell, Paul Lett, Trey Porto, and Ian Spielman, who are part of the Laser Cooling and Trapping Group at NIST, and we're part of the Quantum Measurement Division and the Physical Measurement Laboratory, all of which are parts of the bureaucracy of NIST, an agency of the US government, but we're also part of the Joint Quantum Institute, which is joint between NIST and the University of Maryland. And a little bit more about that in just a moment. And I want to thank the people who support us, the National Science Foundation, the Office of Naval Research, the Army through a multidisciplinary grant. But anyway, let me talk a little bit about the Joint Quantum Institute before starting on the physics. So the Joint Quantum Institute was formed about 10 years ago as a joint operation between NIST and the University of Maryland. And our goal is to study coherent quantum phenomena. And we've got about 30 researchers, and we have lots of opportunities for people who want to do graduate study or postdoctoral study or come as visiting researchers. So just one of those things to keep in mind if you happen to be at that stage in your career that you might be looking for something a little bit different to do for a while. Okay, manipulating atoms with light. So what this talk is about is the exchange of momentum, both linear momentum and angular momentum, between light and atoms, and particularly about the way in which you can use that exchange of momentum to manipulate atoms with light. Now, this invisible part here, written in green, says that I'm going to be telling about this from the NIST perspective, and it leaves out lots of work, including work at MIT and other places where this has been a really important activity. Now, the story of this connection between atoms and light is really a beautiful one. It has a long history, and I'm going to begin with a landmark experiment that happened toward the end of the 19th century. This was the discovery of the Zeeman effect by Peter Zeeman in the Netherlands, and this is the publication of his work in Nature in 1897. It was a little bit after he did the work because it was originally published in German, and then it was translated into English to be published in Nature. But I'm really charmed by the way in which people wrote papers in those days. Look at the way he begins. He says, "The thought occurred to me whether the period of the light emitted by a flame might be altered when the flame was acted upon by magnetic force." Now, translating that into modern English, what he means is whether the wavelength of the light would be changed by being subjected to a magnetic field. Okay, so we have to translate a little bit, but it's just charming to me that he begins the paper by saying, "The thought occurred to me," that as to whether we should see this kind of an effect. So, sure enough, he soaks a piece of asbestos before we knew that asbestos was dangerous. He soaks a piece of asbestos in common salt and lets it dry out, and then puts it in a flame and puts it in a magnet and looks at the spectrum of the light using a spectrometer. And he finds that when he turns on the magnetic field, that the line gets broader. Well, that was, I mean, it was the first time anybody did that, and so that's an important discovery. But he doesn't stop there. He looks at the edges of the line, and he looks at them in a direction along the direction of the magnetic field, and he finds that on one side of the line, the light is circularly polarized in one direction, and that it's circularly polarized in the opposite direction on the other side of the line. And he says, he concludes from this that the atoms that are emitting the light, now remember, this is 1895 or so, right, that he's doing this work. A lot of people don't even believe in atoms in 1895, okay? But what he says is the atoms that are emitting this light must be made up of electrical bits. This is before Thomson discovered the electron. Okay, so this is a pretty smart guy, that he's figuring these things out from the way in which a magnetic field acts on the spectrum of the light. Now, our modern way of understanding this would be like this. We would say that the sodium, because the common salt, sodium was the key thing that was doing the trick. So in the ground state, this sort of simplified energy level diagram for sodium would have the ground state being an S state and the excited state being a P state. And he excites the P state just by virtue of the flame, okay? And so it decays to the ground state, and the P state, having an angular momentum of 1, gets split up by the magnetic field into a projection along the direction of the magnetic field of +1, 0, and -1. But along the direction of the magnetic field, he's only going to see radiation from the +1 state and the -1 state because of the way in which the polarization in the radiation pattern works. And he finds that one edge of the line is circularly polarized in one direction because the light has to take up the angular momentum of the atom. And so if the angular momentum of the atom is negative, then the light's angular momentum is going to have to be negative when you go down to the ground state that doesn't have any angular momentum. And in the same way, if the angular momentum of the atom is positive, then the light that comes out is going to have positive angular momentum. So it'll have opposite directions of circular polarization. And that's what he observed. And understood that there must be electrical stuff inside the atom. This is, what, almost 20 years before Bohr's atom came along. Okay, so he's really understanding some really interesting things about the nature of what he saw. At the end of his paper, he thanks Kamerlingh Onnes for his interest in his work. So this is more than a decade before Onnes discovered superconductivity in his lab in the Netherlands. So this experiment and subsequent experiments and the theory that developed once quantum mechanics, remember, this is before quantum mechanics. This is before Planck, this is before Einstein, this is before Bohr, and subsequent theory and experiments established that light and atoms exchange angular momentum. And you can, well, we'll talk about how the manipulation works in just a few moments. Here, all we're doing is looking passively at the light that comes out, seeing that the angular momentum of the atom is being transferred to the angular momentum of the light. Here's a picture of Zeeman right here, much later in his life when he got a visit from Albert Einstein. Paul Ehrenfest is here as well. So these are some pretty famous names. Now I want to fast forward to the early part of the 20th century, around 1930. A guy named Otto Frisch did an experiment. Boy, it's really hard to see this. So I'll describe what's going on. He's got an oven that is a can filled with sodium metal here. That oven is heated up, and some of the sodium atoms come out through a little hole in the side and make an atomic beam going in this direction. So that's shown schematically here. Then he shines a lamp, a sodium lamp, very much like the street lamps that you have today that illuminate public roads and parking lots, and he takes that lamp and shines it in a direction perpendicular to the way in which the atomic beam is moving. What he wants to see is, can he see the transfer of linear momentum to the atoms? When the atoms absorb that light and then re-radiate it, they're all absorbing in the same direction, they're re-radiating in random directions. He figures it's going to push the atoms to the side. So that's what this schematic shows. He's got sodium light going in this way, and he wants to look for a deflection. Well, here's the data. So the solid curve is what the distribution of the atomic beam looks like as he scans his detector along this direction. He sees this solid line. Then he turns on the lamp and scans it again, and he sees this solid line, and he very cleverly takes the difference between these two lines, and you see that there's atoms missing from this side, the light's coming in from this direction, okay, from the right, so there's atoms missing from the right side that get piled up on the left side. So he shows that indeed this light is pushing the atoms. 1933. I think of Otto Frisch as being one of my historic heroes because most of my career has been manipulating atoms using the momentum of light, and Frisch was the first one to do that. The radiation pressure that he's seeing was seen earlier around the turn of the century, around 1900, by Lebedev and by Nichols and Hull nearly simultaneously in Russia and in the United States on macroscopic objects. In other words, they shine light on little tiny metal foils held in a vacuum and could see that they could make those foils move. But nobody had done it with atoms until Frisch in the early 1930s. Here's a picture of Otto Frisch. From, I think, around that time. He was a nephew of Lise Meitner. Now, Lise Meitner's name you may recognize because she was one of the people who discovered nuclear fission. She and her colleagues studied the fission products of atoms that had been bombarded by neutrons. This is before anybody really knew that fission was happening, and by looking at the fission products they could tell that something had happened in which a heavy nucleus had broken apart into two lighter nuclei. And Lise Meitner should have gotten a Nobel Prize for that, but you know, this was a long time ago and women weren't treated very well back then, and she didn't. Okay, let's go a little bit further into the 1950s. These two guys, Jean Brossel and Alfred Kastler, at the École Normale Supérieure in Paris, invented a process that we call optical pumping. This schematic shows the basic idea in a very simplified way. Imagine that you have an atom that has a ground state that is a doublet S1/2. That is, it's got a spin 1/2 in the S state, and because it's spin 1/2, that spin can be oriented either plus or minus relative to some axis, so it could either have plus 1/2 or minus 1/2, and you're exciting that atom using light up to an electronically excited state that's a doublet P 1/2, and here the 1/2 is the total angular momentum, the sum of the nuclear spin, of the intrinsic electronic spin and the electronic angular momentum. The electronic angular momentum is 1 because it's a p state. The spin is obviously a 1/2 because it's an electron. So you can add it 1 plus a 1/2 or 1 minus a 1/2, and this is the state with 1 minus a 1/2. For an alkali, this would be one of what's called the D lines in an alkali spectrum. But anyway, the point is that I've got two different states, one with positive angular momentum and one with negative angular momentum in the ground state, and I've got a similar set of two states with positive and negative angular momentum in the excited state. Now let's say that I shine in light that has positive angular momentum and excite the atom. Well, that angular momentum has to go into, the angular momentum of the light has to go into the atom. So that means that if I start from m equals minus 1/2, the only place that it can go is m equals plus 1/2 because it's the only state that has more angular momentum than the ground state. And the light has angular momentum, so it has to go someplace. Now, that m equals plus 1/2 state can decay back to the state it started from, in which case we just do the whole thing over again. But it can also decay to the other state, the one that has positive angular momentum. And if it ends up here, you cannot excite it again. In modern language, we would say this is a dark state. It can't be excited by the light because you see the light has positive angular momentum and it tries to excite it to something that has more angular momentum, but there is no state there with more angular momentum, so the atom cannot be excited, it's dark. So the upshot of all that is that if you shine experiments but when you say it with atoms, somehow it sounds like pointing vectors is pointing like that, an integral multiple of 2 pi, or it's not all, instead of a maybe. It depends